Hello, my name is Chigozie Ofodike, and my project is signal processing for fault modes detection and classification. For this research, I was mentored by Dr. Rob Edmond, Dr. Kyle Miller, and Dr. Arthur Dabrowski. Introduction. Signal processing analysis is a facet of data analysis and machine learning that focuses on the acquisition, analysis, interpretation, and manipulation of signals. These signals are generally gotten from sensor equipment. For our specific focus, we choose to analyze medical sensor data. That is data aggregated from the standard 12-lead ECG system. Our goal is to detect known fault modes of this complex system. The overarching end goal is an automated system capable of performing the detection, classification, and alert. And this presentation is as follows. We present our approach, the benefits of this research, the current standing of our results, our conclusion, and our future work. The next steps. Then we present our references and give proper acknowledgements. First off, motivation. Why is our research important? A cardinal rule of the data analysis, machine learning, and information gleaning pipeline is that if the quality of the input data is poor, so is the quality of the information gleaned from it. This concept holds true in both in the research space and the practical use systems. Our goal is to be able to detect and classify this specified faulted data quickly and effectively. In our context, there are many types of potential faults in the ECG sensor data. And understanding that this is a short research time, we choose to focus on only some of them. Our focus is the inconsistent standard deviation pictured here, and then the zero line fault mode. Next, our approach, how we do this. First, it's imperative that we understand the data. As the first step to most data analysis process, we must first understand the data, and this is done through deep data exploration. In doing so, we set rules as to what is faulted versus what is normal in our context. Then we generate synthetic data. A cardinal rule in the machine learning pipeline is to test and train on completely different sets. For our training, we choose to generate synthetic data similar to our explored data. This is done with the help of CMU's Artan Labs NeuroKit, an openly sourced software. And then from the normal synthetically generated data, we can then manually implement our fault modes similar to those that fit our criteria. For instance, here we have a real fault mode, the real inconsistent standard deviation fault mode, and then here we have our attempt to synthesize that specified fault mode. Obeying the cardinal ML rule mentioned above, we then build our model based on the synthetic data set and test it on the real data sets. We iterate in this process while fine-tuning our model built on the synthetic data sets. Next, benefits. What are the benefits of this research? First off, this system will ensure that high quality data enters the pipeline for both the research and industry practitioners. We hope to build a data-aware AI capable of automated classification and detection. In an industry context, we hope to be able to differentiate between a real medical emergency, i.e., a very sick patient, and failing medical equipment. This allows better allocation of the resources available, meaning we can save money, save time, and better assist practitioners in the field. Results and model performance. For our model performance, we compare 4 different models: a random forest built on the normal versus standard deviation, a random forest model built on the normal versus zero line fault line, and a random forest built on the standard deviation and the inconsistent standard deviation versus the zero line. And finally, a linear regressor built on the normal versus the standard deviation. And these are all built on, again, on a synthetic data set. In the middle, we have a standard ROC curve with false positive rate on the x-axis and the true positive on the y-axis. The plots on the left and right are log scaled with a focus on practical utility, namely a low false positive rate, and a high true positive rate. Future work. For our future work, we hope to better understand the discrepancy between our real data set versus our synthesized data sets. We hope to implement, detect, and track more fault modes. We also hope to complete the entire detection, classification, and alerting pipeline. These are references. And for our acknowledgements, this research is based upon work supported by Carnegie Mellon School of Computer Science and Robotics Institute. We thank the Robotics Institute Summer Scholar Programs for making this experience possible. We also wanted to give a specific thanks to Rachel Beerson and John Dolan. Also, thanks to the members of the CMU's Autumn Lab for their constant guidance. Thank you.